Good afternoon, everybody. Welcome to the first of the fall CCOM seminar series. I'm Kevin Jerem. I'm one of the master's graduate students here, and I came to UNH for my undergraduate degree in mechanical engineering. Graduated in 2007, and spent a couple of years doing other engineering jobs before I decided to come back. I'm working with Tom Weber on imaging methane seeps using a fisheries echo sounder. And Chris and I are the hosts this fall, and we will be in the spring, hopefully, too. So I'll let him introduce himself, and then he'll introduce our speaker for the first seminar. Thank you.
Yeah, thanks, Kevin. Yeah, so my name is Chris Engler. As Kevin said, co-coordinator for the seminar series, and it's my honor to have Val be our first speaker. I want to thank him for kicking off this seminar with someone who was familiar with the whole process, so we can kind of take a baby step and learn the whole thing. But that being said, on our whole list of speakers, we should be very proud that Val is definitely at the top of our list of people that we would have invited anyway. Val got his bachelor's degree in physics from the University of the South in 1994. Spent some time in the Navy as a submariner on the USS Hawkbill. Did some time in private industry for Quest Communications, also worked for Lamont Doherty Earth Observatory. Then did his master's degree in ocean engineering here at CCOM in 2008. Now his research foci are seafloor water column mapping from AUVs, sensor development, and sonar signal processing. And today he'll be talking about integration of geometrics magnetometer into Teledyne Gavia AUV. Thank you, Val.
Thanks, Chris. I'll try to set the bar nice and low so that everything else goes really smooth. So our lab has a collaboration with Trembanis at the University of Delaware, and he owns a Gavia AUV. And so this work is work that he has done, basically, and I'm his kind of chief engineer, so by proxy it's work that I have done as things roll downhill. So Art got a grant from the Department of Defense under this program called the Environmental Security Technology Certification Program, ESTCP. I don't know how that you say that, but anyhow. It's a program in the Department of Defense that seeks to develop new technologies and integrate new sensors and do new things to address environmental concerns to the Department of Defense, and there are sister programs in the Department of Energy and Homeland Security, and this one was to integrate a magnetometer into an autonomous underwater vehicle. The team of people involved was Ryan Steigerwald, it's a great last name, from a company called Weston Solutions, and they do environmental surveys of all different kinds, but they do a lot of explosive ordnance kinds of stuff, which is one of the things that you would use a magnetometer for. Of course, Art is kind of the principal investigator of all of this, and the folks from Geometrics were Ross Johnson, George Tate, and Misha, is this pronounced Turnichev? I think that's right. But these are all, it was a great team and great guys, and a lot of fun to work with. Misha, I can imagine crossing Yuri with like Winnie the Pooh. He's a great guy. I really enjoyed Misha a lot. He's the resident geophysicist.
I'm trying to picture this.
So, in summary, we could just close it up right now and go home if you want. Like I know it's Friday afternoon, but this is what we did. So, why would you want to put a magnetometer on AUV? Well, after World War II, the U.S. dumped lots of munitions to get rid of them, and some of them were filled with mustard gas and other nasty things, and a lot of it was dumped off the coast of the U.S. in the ocean, some of it in lakes. Other countries have done similar things. We're not the only people. In 2010, a fisherman hauled up mustard gas containers. This made it all the way to the packing plant. Just last summer, the same thing happened again. These were articles out of the paper from describing a boat that was going and dumping a bunch of this stuff off of the Atlantic coast. So there's lots of stuff out there, and it has caused harm, and so the Department of Defense is interested in trying to do something about that. Now, we've talked actually with commercial fishermen about this, and they tell us that they pick up this stuff all the time, and it scares the bejesus out of them, but they don't want to tell anybody because then they have to do something formal about it, so they pitch it overboard. So all the places that this stuff is likely dumped may be spread all over the place. but that's sort of another issue. There's other things that you could use a magnetometer for, that you do use a magnetometer for in this kind of an application: marine archaeology and pipe tracking and marine salvage, that kind of stuff. So let's talk a little bit about the AUV. It's about almost 3 meters long and weighs about 180 pounds, 77 kilograms, something like that. In the front here, we've got in the nose cone, there's a collision avoidance sonar and a downward-looking camera. Of course, we didn't have that part installed for these missions because that's where we put the magnetometer, right in the front. I should point out this is modular, so every place you see a seam there, these things all come apart. You can mix and match things and put it all back together. The battery is here underneath the handle. The INS and Doppler velocity log is a navigation system. Behind that is the control module that's got sort of the brains of the operation, the computer that controls everything. There's a Wi-Fi in there and a GPS and a satellite iridium phone for communications, an acoustic modem in there, and a side scan. Behind that, installed in this image is a geoacoustics geoswath for seafloor mapping. Of course, we didn't use that for these applications, and so we just popped that guy out of there and pushed the control module forward and buttoned it all back together. The sensor that we integrated is this Geometrics G880, a self-oscillating alkali vapor optically pumped magnetometer. It's a big, it's a lot. There's a lot there. And actually, I think this is kind of interesting, so I'm going to force you guys to sit through how this thing works as best as I can explain it. So the alkali vapor it uses is cesium, and here's cesium on the periodic table, and you'll remember from freshman chemistry that cesium's got one electron spinning around the outside, and it tends to be reactive with lots of other things. And if you excite that electron with the right frequency of light, you can push it from the slowest orbital into another orbital up above it. But it also has a couple of other energy states that are worth mentioning for this application, and one is the electron magnetic moment. So from your quantum physics studies, you'll remember that electrons have spin, magnetic spin, and they actually don't physically spin, but they have all the characteristics of something that's spinning, a charge that's spinning. And it's quantized in +1/2 and -1/2 increments, and in the lingo of quantum mechanics, people talk about spin up and spin down, so I might use those terms. But that creates two separate energy states down at this ground energy state. And the cool thing about these energy states is something called the Zeeman effect. I wish I like the Schmidt effect, it just doesn't have the ring, but it's a great name. But the Zeeman effect is that these energy states that result from the magnetic spin of the electron in that outer shell are dependent upon the magnetic field, the ambient magnetic field that the atom is in. So these states, these two states, change their energy levels. Now, you see all this hyperfine structure in there. That kind of complicates the issue a little bit. That's interaction between the electron magnetic moment and the moment of the nucleus and the angular momentum of the atom, and it gets way confusing. But all you really need to know is that these energy levels, if you went from sort of the ground state of this one to the ground state of that one, it's dependent upon the magnetic field. And that's essentially how the measurement is made. But let's see some of the mechanics. So in this magnetometer, there's a light source, a filter, a cesium absorption cell, and a photomultiplier. And the first step is to get all of the electrons in the outer shell of these cesium atoms in this absorption cell into the same spin state. So like all spin up, for example. I actually don't know if it's spin up or spin down. But the way they do it is they take this filter is a circular polarizing filter, so you might know that you can polarize light like vertically, and you can polarize it horizontally, and you can send it through a filter that makes it circularly polarized as it goes. And if you do that, and this absorption cell is in an ambient magnetic field and aligned more or less in the right way, you can excite the atoms from the ground state into this next orbital, but only do it preferentially out of one of the two spin states. So maybe all the spin up guys get excited out of the ground state up. And when they fall back down, they fall back randomly, but if you are only pumping the ones that are spin up, and then when they fall back down, some light's emitted, then you can do it again and again, and eventually you'll get everything into one spin state. So all of them are pointing up, if you will. And when you do this, you have that light coming into the absorption cell, and on the far end, you have a photomultiplier that's measuring this light, and every time the light excites an electron up into this upper shell, and the electrons drop back down, more light is given off, but it's not collimated the way this light is. It scatters in every direction, and so the light that's measured by this photomultiplier dims. And so you could imagine if you're the photomultiplier and you're watching this, when the light stops dimming, you know that all of the electrons are up because there's no more to flip. And so you know that everything is in one spin state. So once you get it into one spin state, then the next thing to do is flip some of them into the other spin state. And the way that's done is with more light, in this case an RF pulse. It's not as high energy a pulse as the other process is the optical pumping part of that big discussion. This is a lower frequency light, and it's tuned to flip the states from one spin to the other. And you'll remember that that was dependent upon the magnetic field strength. So you could imagine sending a sweep of RF pulses in there at a bunch of different energies, and the only one of those pulses that's going to affect those electrons and spin them from one state to the other is going to be the one that matches the ambient magnetic field state and the energy transition between those two. So if you're watching this from the photomultiplier at the end, when you send the RF pulse in, you have a furrowed brow. I hope this is getting through.
It's a good one.
Okay. So you're sending this RF pulse in, you're flipping some of the spins, the optical pumping resets the whole thing, and you monitor it from the photomultiplier at the end. And you know when the light dims that you got the right frequency, because when the light dims, that means that you got the right frequency to flip some of the electrons from one spin to another, and then the optical pumping could do its resetting, and that's what you're actually detecting is resetting.
Are they using the laser to excite at the beginning, a single frequency laser?
No, it's a different kind of light source, and I forget what it's called, but it's like a discharge lamp kind of thing. This is this light source at the beginning, and then there's a filter that filters out everything but a very specific frequency, and then another filter and a collimating lens to get it all going in the right direction and do the circular polarization. But I don't think there's a laser in the thing. Other magnetometers sweep the RF frequency the way I just described, and Geometrics doesn't actually do that. What they do instead, and I don't fully understand why this happens the way it does, but what they detect with the photomultiplier down here, this whole effect, gets modulated by the RF signal that they put in a way that they can extract it out and amplify it and use it like in the RF excitation on this end in a way, in like a closed looped kind of thing, such that it automatically tracks the frequency that's required to flip the spin states. And I maybe haven't explained that terribly well, and I'm not sure I fully understand exactly how the light in there modulates this signal, like how that gets passed all the way through, but we can get the Geometrics guys to come explain it to us at some point. But that's the big flick of how it works. So what you actually measure is the RF signal in that closed looped kind of tracking algorithm, and you get two numbers out. One is the magnetic field, which is just proportional to the frequency of the signal that you put in, because that's the energy required to make that spin state transition. And then you also get a sensor amplitude value, which is the amplitude of that RF signal, and it just kind of tells you that everything is working okay. Like if this goes down to 0, then you don't have anything actually to measure, and you know that this value is meaningless. Okay, so it turns out that the orientation of the sensor with respect to the ambient magnetic field is important in the way this works. There are dead zones in the sensor in places like a hollow cone for which it's sensitive. So depending on where you are on the Earth, you have to orient this sensor in different directions to get a good measurement. It doesn't actually affect the measurement that you make. It just affects basically the amplitude of that sine wave that you're measuring. So it doesn't affect the frequency, it just affects the amplitude. And then there's other things that cause problems. A big local gradient in the magnetic field causes the whole process to just get wiped out, and that sensor amplitude goes to nothing. So if you are on a ship that's got a lot of iron on it, then the whole thing doesn't work. Or if you happen to be close to a big ship that has lots of iron on it, the whole thing doesn't work. Or if you're on a pier that has rebar running under the concrete, or a big bollard on the side, or if somebody happens to be standing next to the sensor with a watch or a cell phone or a set of keys, all of those things can make things go haywire. And when you're trying to figure out what's wrong, that can be very frustrating. So it's a very sensitive gadget. So we should talk a little bit about magnetism so that we're all sort of on the same page. And the first thing that you probably need to know is Ampere's law, and that is that whenever you have an electric current, it creates a magnetic field around it. And a magnetic field, when we say magnetic field, what we're really talking about is magnetic flux density, and that's this value B. And just to give you a sort of a feeling for numbers, if you put one current in there and 1 meter away, and stick all the constants in, you get a number that's 2 times 10 to the minus 7 Teslas. It seems like a really small number, but as you'll see, this is kind of a big value. Tesla is in Webers per meter squared. That's magnetic flux density. And like I said, this is a big number. Frequently, people use nanoteslas. That's what actually comes out of the magnetometer, are nanoteslas. And a gamma is 1 nanotesla. This is like an old unit, but it's in a lot of my slides because of some of the older documentation, so you'll see gammas a lot. 10 to the 5th nanotesla is a Gauss. That's another kind of older unit, but frequently used. So, of course, you can't have a presentation like this without making fun of your boss and how many Webers there are in his office. This is also quantized, by the way. So the next thing you need to know is magnetism in objects. So objects can have intrinsic magnetism, of course. So their molecular makeup is such that there are dipoles that tend to be aligned in one direction, and they produce a localized magnetic field. But you can also have induced magnetism, in which the molecular makeup is such that the dipoles can move, and when they're in an external magnetic field, they all tend to align in one direction or another, and that sort of reinforces the localized magnetic field. Iron, of course, has both of those properties, and so it's particularly sensitive. And things with high magnetic susceptibility tend to warp the ambient field lines around it and concentrate them in a way that that's frequently detectable. So the total field magnetometer isn't like magnetic fields are vectors. They have a direction and an amplitude, but the total field magnetometer just measures the amplitude part. It doesn't matter about the direction at all. So the nominal magnetic field for the Earth is something like 50,000 nanoteslas or 50,000 gammas, and a reasonable magnetic anomaly that you might detect is something relatively small compared to that. It's just like 10 nanoteslas. So what you're actually effectively measuring is the projection of this local disturbance in the direction of the magnetic field. Of the Earth's magnetic field. What you're really measuring are deviations in the Earth's magnetic field with this thing. Out of Geometrics has an applications manual, and it's got some nomographs in here to kind of give you a feeling, and I just thought I'd give you a feeling about what kinds of things make different anomalies. So like a pound of iron at 2 meters away is maybe 3 nanoteslas, 3 gammas here. Or a screwdriver at 5 feet that have 5 to 10 gammas, or a revolver, or a 38 special, or a 45. I think that's kind of funny. 5 feet, 10 to 20 gammas are nanoteslas. So you can see there's like, so DC train, 500 feet. So I guess this isn't the kind of train you got at Christmas time. But yeah, so cow magnet. I'm not even sure what a cow magnet is. Does anyone know what a cow magnet is?
I feel like a cow eats a piece of metal.
Yeah, thanks. Okay, so magnetic fields have 2 poles, right? A north pole and a south pole. And like theoretically, there's no such thing as a monopole, but it's possible that you can have a magnet that's so long that you only detect one side, and so you effectively see what looks like a monopole. And And when you have a dipole that's arranged in this direction or a monopole that's arranged that direction and the ambient field is like this, what you see spatially in the observed Earth's magnetic field are sort of this concentration of magnetic field lines around those things. And of course you can have monopoles that are like a whole bunch of them lined together, and it kind of looks like a line of monopoles of negative end of the magnetic field, or a sheet of them, and dipoles can be arranged in a similar kinds of way, and these give you different magnetic signatures. Of course, the depth of an object of a dipole changes its response as you see it above the top. And if you do a measurement right over the top and then do a measurement off to the side, of course, that has the same kind of effect, right? It tweaks your measurement. And in there, because a bunch of what they do is geologic in nature, they've got all of these nice diagrams of different kinds of structures that have magnetic properties, maybe iron seams or whatever on a geologic sense, and they produce these kind of characteristic curves for what's there. And of course, the effect of this falls off as a function of distances that you are away. And it falls off as the cube of the distance for a dipole once you get far enough away from it. So if you measure something at 2 meters and then you go to 4 meters, it drops off by a factor of 8. And that can be a big deal because you kind of got to get close to stuff to see it. The Earth's magnetic field varies spatially, and that's not such a big deal, actually. I mean, it's good to know, but and the magnetometer can measure the full range of all of those. This is in nanotesla, so 25,000 nanotesla up to 60,000 nanotesla. But what's challenging is it also varies temporally. And every day the sun heats up the Earth's ionosphere and causes a local oscillation, a diurnal oscillation in the ambient local magnetic field. But to make matters worse, some spots and micropulsations and stuff happening with the solar wind also cause changes, and these things can be changes on the order of tens to thousands of nanoteslas on scales from just a few seconds to days. That's a 10-minute stretch there. This is a 1-day stretch, but the scale of that is 50 nanoteslas, and that one is 10 nanoteslas. So all of this sort of compounds to the measurement that you're trying to make. So we put up a base station, and you can't just put a base station up anywhere, right? It's got to be a place that is pretty magnetically stable. Like, you don't want to put it next to a road because a car will go by and you'll get a big blip. And you don't want to put it, I mean, this is the same sensor here that we're putting on the AUV basically, so you can't put it in a place that has a really strong magnetic gradient because it won't work for the same reason that the other one doesn't. So you got to find a park and keep the kids away and all that kind of stuff, find a place to put that thing. And if you're doing work, of course, on an AUV, your base station can't be on the boat because the boat's going to have too much magnetic stuff, so it's got to be someplace on shore. So that can be a limiting factor a bit to what you can do. But what about the AUV itself? Turns out it has its own intrinsic magnetism and its own induced magnetism induced by the Earth's magnetic field, and electric currents, of course, running through the AUV, and eddy currents. Those are currents that happen in the hull of the AUV due to the ions going by. And these things are ambient field dependent and vehicle attitude dependent in the Earth's magnetic field. They're battery charge state dependent, they're time varying, and they can vary by tens of nanotesla, like bigger than the signal that you're trying to measure. And that just makes me cry.
That looks like a cross between Yuri and Winnie the Pooh.
Yeah, right. So thankfully we're not the first people to have dealt with all of this stuff. And the folks who do this for a living do what's called magnetic compensation. And it's a process of coming up with a bunch of terms that allow you to filter the raw measurements to correct for as many of these things as you possibly can. And there's a seminal paper by this guy named Paul Liliak, and I'm sure there's more recent papers than this on the topic, and this is just one of the tables out of his paper. This one's signal to source ratios for roll maneuvers as a function of heading. So this was for corrections for a magnetometer on a plane where they have similar kinds of effects. This is all about permanent magnetism and induced magnetism, but not about time-varying current induced magnetism, which was something totally new and not handled by any of the software that Geometrics has. So that was a whole new thing for us. So what they did is they built this cart knowing that this was coming, and they put these current coils on the cart in two directions with controllers and a data acquisition system. And actually the only thing that's not actually on there, I think, is the magnetometer in this picture. But they put the magnetometer on there as well, and they rolled this guy around. And they produced data like this, and the red is the raw data coming out of the magnetometer. And then when they used their standard compensation software that removes all the effects for permanent magnetism and induced magnetism, they would get this green curve. And then for the first time, they added in the effect of like measuring the current going to those coils to correct for that as well. And they produced the blue curve there, and you can see it's quite a bit of improvement.
Hey, Bob, can you see what the magnitude is there? I can't hear you.
Yeah, sorry. This is that's 50 nanoteslas. That's 50, and the value is 48,500.
Thank you.
Yeah.
Did the size of those coils on the test cart resemble the coils you see in the AUV, or
No.
does that matter?
I mean, it probably does matter, but no. It was just a test and an attempt to make sure that they understood the math and the math worked, kind of thing. So the kind of technical approach for installation was to install the magnetometer and the AUV, and they also added a flux gate compass. And the reason they use this, of course, this is a magnetic sensor as well, right? But and this is actually a vector sensor in 3 directions, but it's nowhere near as sensitive as this guy is. And the only reason that this was there actually was to get the attitude of the vehicle, its heading and pitch and roll relative to the Earth's magnetic field. And you might ask yourself, okay, you got like $100,000 inertial navigation system on there. Why are you going to use this instead of the INS? And I asked that question, and they felt more comfortable with this. And it turned out that this works better than the INS, and I'm not 100% sure why. And it might be because this is, the INS is making measurements relative to gravity and to a local coordinate system, where you really need measurements relative to the Earth's magnetic field vector, both its direction and dip. And this makes those measurements directly. So it could be that you make the measurements with the INS, and that coordinate system transformation just isn't perfect, and or maybe not localized enough, or the model used for it isn't good enough. I don't know why it didn't work, but it turned out it didn't work as well. So they had a bunch of questions going in. What were the significant sources of magnetic interference for an AUV, and what's the best model for an AUV for doing these compensations? And what's the best way to obtain compensation coefficients? Like, what's the best kind of pattern do you run with the AUV? How do you best do that? And how are they best applied? And they talk about improvement ratios when they talk about compensation coefficients. And that's kind of a measure of sort of the RMS noise level before you compensate the data to the RMS noise level afterwards. So this is what was built. There's a pressure vessel here for all the electronics, and then a flooded section and a nose cone on the front. And of course, it's way out in front of the rest of the AUV, so you can try to get away from all of the things that have iron in them in the back that might produce magnetic signatures. And all of the components in here are either plastic or they're made of aluminum, one of the two. And aluminum that's gone through a process of measurements to make sure that it doesn't have residual iron in it, doesn't have a residual magnetic signature. In fact, there was a set screw up here that was causing problems with the sensor at one point, little tiny couple millimeter long set screw. This is what it looks like in real life, and there's art taken out of the bag. And this is a picture looking down the end. That's the sensor, so it's about the size of a Coke can, roughly. And Art with his baby. And this is like the electronics on the inside. Nothing terribly interesting there, I suppose. So our first field test was at the Naval Academy, and the only reason we went to the Naval Academy was because Art's AUV was in Brazil doing commercial contract work, and the Navy, the Naval Academy actually has a Gavia, and so we asked them if we could borrow it for some tests, and they allowed us to do it. And this was a neat trip. It was fun to go to the Naval Academy and see all of that stuff, but it was a frustrating trip because, of course, it's like the first field trip and nothing works right? So their AUV was having communications problems in the communications conduit in the middle, and we had a really hard time talking to our sensor, which was at the far end. And then we had other problems. There was an electronics problem with the sensor that, of course, was intermittent. It would come and go, and things would work, and then it wouldn't work, and we went round and round with that. And so we had a couple of days to do things, and in the end, we had hoped to run missions out in the bay, and we didn't get a chance to do that. We did get to run the thing around the parade ground, and we were hoping to collect some data that we could use to test the compensation effect. So this was just like us lugging this thing around the parade ground. And of course, when you do a compensation mission, a mission to try to create these compensation coefficients, you got to do it in a place where there's no anomalies. Like, it's got to be benign in the background. And of course, there's a giant anomaly in the middle of the parade ground. So there's a conspiracy theory waiting to happen. What is under the Naval Academy parade ground? I think it's just a drainage pipe, but there was a big one there. So that wasn't terrifically helpful.
Art asked Jimmy Hoffa.
Yeah, that's right. Thanks, Art. Can you make that go away?
Oh, yes.
Can I make that go away? We did get to verify the ballast. Most of this is air, obviously, so we had to put lead in there to make the thing neutrally buoyant. And I did all the calculations for that. I am very proud to say it was spot on, or I can, because I didn't think it was a pain. But this was us, I have more pictures of me hanging over a dock, manhandling the AUV, but there it is. I went to trade it in for a torpedo, but Art wouldn't let me. So our next field site, that was in October of last year. The next one was in December, and this is Lewes, Delaware. So this is the Delaware Bay, and Cape Henlopen is over here someplace. Atlantic Ocean is out there someplace. And University of Delaware's marine facilities are right in here. And so again, our sort of thrust was to make everything work, make all the data logging work, go out and run some missions and try to get a feeling for, we had no idea, if you put the rudder over, does that change the effect that you see on the magnetometer? Is any of that stuff going to work? Can we collect data that we can produce some of these compensation coefficients and then apply them and see what kind of improvement ratios we get? So we put it out in a field. This actually was field testing, just to kind of get some baseline data. And of course, there's a backhoe dumping sand over here, and we could see that signal. Every time the backhoe comes and goes, we get this big blip of the signal going by. So it works, but wasn't what we were looking for. So it was cold, of course, and we did get in our little boat, that little 5-horsepower motor, and there was quite a current running in the channel, and were closed up for the year, wussies. But so they didn't. This was actually not the marine facility's boat. We had to go borrow another boat, and we didn't go out in the bay. We ran missions in the bay, and there was quite a current, and so we only ran the missions downstream because it was just too hard to try to run the AUV upstream in this. And we collected some data, but didn't actually get to collect the compensation run data. And our day was cut short. Well, this is, Nicole is a grad student of arts. This is her and me sleeping at the wheel, it looks like, doing AUV missions. And this was just our track lines over the course of the day. And I only put this up here because this little point down here is where our engine broke down. And then this was try to start the motor, 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 paddle, 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 walk, 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 walk. And that was the end of our field site on go number 2. It was a bit frustrating, and it was the end of a very long day, and you can see it on Nicole's face as I was walking back to get help. And so we went to Touch of Italy and had a very nice pastry, which I completely recommend you go to if you get a chance while you're there, Jonathan. So we made some progress. We sorted some things out. One of the issues, so that whole signal coming and going away, we thought we had narrowed that down to the INS. So in our first configuration, we had the INS right next to the magnetometer, and we thought the INS was causing a problem, like producing a localized magnetic field of some kind and causing a gradient that was so big that the sensor would stop working. So we moved the INS to the back, which you could do, and had the battery right up next to it, which is counterintuitive because you think the battery is going to cause a problem as well. It turns out our theory was wrong. The problem was totally different. The INS, and we don't think the battery either, causes a very big effect, but problem was an electronics problem in the way everything was sort of pieced together, and we sorted it out in the end. So our next field go was a field demonstration in St. Petersburg, Florida. And this was in March of this past year. And we contracted with SRI, which is a company kind of like SAIC, like the scope of the stuff they do, if you're familiar with SAIC, is very similar. And they have provided like field sites for other folks doing unexploded ordnance kind of work before, so they were familiar with all of this. This is their facility right on the pier. It's a really nice facility, lots of space, a really big lab space, plenty of gadgets and room for us, and boats nearby, and there I am over the dock again playing with the AUV, but boat support. So they provided all of our boat support. The other thing they did is they laid out seed targets for us, 60 millimeter all the way to 155 millimeter mortar shells, and laid these out in about 10 meters of water. The little ones they put on cinder blocks, and the big ones they put on plywood so they wouldn't sink into the mud. And they had a coil of rope and a timed release with a float. There's one of the floats on it. So they deployed all of these. They took some video of it for us, so we could see it how it was deployed and what it looked like. And they put them out in a grid. So this, you can't see this probably, but it's 100 meters by 100 meters, and they're spaced about every 20 meters apart. And there was a calibration grid and a blind grid. One for us to play with where we knew where everything was, and the other one where we didn't. And then they went and surveyed this in with a blue view, 1.2 megahertz blue view, with RTK GPS and an F190 Coda Octopus INS. And I have to say, like, they did a great job, and they probably got positions to all of these. They could detect those floats without any problem to like 10 centimeters or so of uncertainty. And this was a pole mount gadget that they were putting on another boat that they were able to deploy really quick. And like, I totally think like that this is a gadget that we should have a little guy like this that we can like put on a boat and just go and do a survey like this, because we don't actually at the moment. I think this would be a cool thing. He's not even paying attention. So we had a bunch of performance objectives, and some of these things were realistic and some of them weren't. But they were what they were. So depth keeping, height above the bottom, we wanted to not vary more than 1/4 of a meter. Well, it was very flat out there, and we passed that with no problem. Roll and pitch of the vehicle, we didn't want to vary more than 10 degrees because it's important to kind of keep the sensor in a known configuration for compensation purposes, and that was easy to meet. A long line measurement spacing, we wanted no more than 1/4 of a meter apart between successive samples, and that was easy. We just had a high enough sample rate. That was a problem. Survey coverage was a little bit of a problem. We wanted our line-to-line spacings to be just a meter apart, and we didn't meet that, and I'll explain why in a minute. I'm going to build suspense. We wanted everything positioned to like absolute positions on all the targets to less than a meter. And although we claim that we passed this, we kind of cheated to do it. We can do it, but not the way I wanted to do it at the beginning, and I'll explain that in a minute. And the improvement ratios and the calibration coefficients, actually we passed that as well. So I'll show you what all this looks like. So we've started off doing compensation missions in the beginning. This is kind of what a compensation mission looks like. The scale of this is like, that's minus 100 to plus 100 meters. So the diameter of this is about 100 meters or so. And the idea is to induce pitches and rolls in the vehicle that's kind of bigger than what you're likely to do in a standard mission, so that your compensation coefficients cover all the possibilities and work. So this kind of shows you the effect. The blue is the pitch of the vehicle, and this is the scale on this side. So this is minus 12 and plus 6, I guess. So the average is a little bit pitched down. The vehicle is positively buoyant. And then the red is the magnetometer signal after the diurnal compensation, so the base station compensation, but without anything else. And then the totally compensated curve is in green there. So you can see that pitch actually has a big effect. The red is the pitch is still in there, but the green is completely taken out. Roll, on the other hand, doesn't have so much of an effect. The blue again is the roll. This is a smaller scale on this side. The vehicle doesn't actually roll very much except for during the turns. And there's no real signal in the red that you see in the blue, like that high frequency stuff there isn't in the red. So roll's not having very much effect on the measurement in this case. Heading certainly has a big effect. As you make big swings in heading, the red changes all around, and the compensated version of that, the green, takes that out. Now you'll notice if you look at this close, there are these little step jumps in the green. Those little tiny step jumps are the acoustic modem transmitting. So every time the acoustic modem transmits, it's drawing quite a bit of current, more than an amp, and it's producing a localized magnetic field that's being picked up in the magnetometer. So this was its compensation between using the INS and the flux gate. And the flux gate is in blue there, and the green is the INS, and the red is the raw. So you can see kind of visually that there's less funky stuff going on with the flux gate than there is in the INS. This is all Misha's work, I should say. This is all his doing. So this was comparing different compensation strategies. The red is the raw field. The blue is only considering compensation terms that deal with the permanent magnetism of the vehicle, but not the induced magnetism. The 5-term one, that's the magenta, and you can't see the magenta because it's right underneath the black there. That includes induced magnetism within the vehicle and compensation, and then the black are all the currents. So there's not much difference between the 5-term and the all the terms one. The big difference is, there's certainly an effect from intrinsic magnetism of the vehicle, but the induced magnetism also is really big. And if you zoom into some of that same data, this is the effect, and so you can see that there is a little bit advantage to using all terms. That's the black curve there. You can ignore the original code. They transferred their code from Fortran to C++, so they were testing that to make sure they were getting similar results. So current in the vehicle, the electrical current coming out of the battery, is something that we can measure. And Misha looked at that as well and found that there's a time lag in our current measurements by a couple of seconds. So I don't know if you can see these numbers, but it's like minus 10.4 there and minus 8.4. So the numbers that come out of the Gavia are negative. So these are higher current values on the bottom, and that's the red curve actually is the current. And the magnetic field is the blue. So you can kind of see that this step there should correspond with that increase in current, and it doesn't. And here he's just shifted them down there. And then included the current in the compensation after the time shift. So the blue includes the current and the red doesn't. And it doesn't have a really dramatic effect. It does help things a little bit, but the scale here, for those of you who can't see, so the scale on these previous guys, well, those are tenths of nanotesla, but this is 5 nanotesla there. So that's quite a dramatic effect. But the scale, on this, there you go, this one is just 0.2 of a nanotesla there. So this is much smaller scale. This we're looking at the fine in the weeds. Okay, so turns out the challenge with this compensation coefficients is that you couldn't just measure one and apply it universally to everything you were doing. Not universally for a given battery, not even universally for a given battery charge. So you could run a compensation mission and produce a set of coefficients, and then run a production survey, or try to use those for a different production survey, maybe on a different day or a different time, and it completely wouldn't work. And you can even take the production survey data and create calibration coefficients from it, like from the turns and the stuff that's outside the part that you're measuring, where there aren't magnetic anomalies. And that's what he's done here, and those work pretty well for the survey itself, but then don't work well for the compensation data from the day, in this case, the day after. But so what's going on there is that it's different charge states of the battery. So again, this is current coming out of the battery, and it's 10.5 amps down here and 7 amps at the top. And these spikes, those are the spikes from the acoustic modem. So we're transmitting pretty frequently telemetry information over the acoustic modem. And later on, we stopped doing this because it's just kind of a mess. But you can see that in this part, the So you have a fixed amount of power that you need to drive the AUV, and over time the battery voltage drops, and to meet that current demand, to meet that power demand, the voltage times the current equals the power. So as the voltage drops, the current increases. So you get different amounts of current coming out of the battery at different charge states. So this is just a difference of two different charge states with sort of, over that period of time, relatively stable current coming out, but very different amount of current. So the compensations, and what this looks like from a compensation point of view is it's a static current. I mean, like the average there is kind of a static value. So when you do the compensation calculation, it gets confused with the intrinsic magnetism of the vehicle. It looks like a permanent magnet that's in the vehicle, and so the compensation that you're doing, even when you include the current terms, because of that confusion, it doesn't apply universally through the entirety of a battery charge. So it means that there's some nuance into how you calculate the compensation coefficients and how you apply them in emission. So this is what it looks like when you have an uncompensated field and you sort of grid up the data, and this is what it looks like when you do a measurement and compensate. You can see there's quite a dramatic effect there, and you can see there are anomalies there from stuff. So part of our goal in doing this was to have good navigation. I mean, in theory, people are going to go out and retrieve the things that we detect. So they need to go out as divers to have a pretty good idea of where things are in an absolute sense. So we wanted to be able to find targets in an absolute sense to less than a meter. And how do you do this with a vehicle that has a WAS-enabled GPS with a 5-meter uncertainty right from the get-go, and then an INS and a DVL that nominally grows as a 1/10% of the radial distance that you've traveled? So I was not sure how this was going to work, and in the end, it certainly didn't work the way we had talked about it before we got there. But what we were thinking to do was take an RTK GPS and put it over the vehicle, and we can push those fixes into the INS separately from its own GPS and try to remove as much of this error as absolutely possible. In the end, we couldn't do that, and the reason was largely probably my fault. I just didn't know how to turn off the positions coming from the Gavia's own GPS. So as soon as I removed that external GPS, then the position information was going to get corrupted by what was coming from the vehicle. And you could have tried to push the vehicle down underwater to prevent that, but it wasn't logistically a possible thing for us to do. The other thing was to place detectable items on the seafloor, survey them in, which of course we had all of those seed items, and all of them were surveyed in, and then to detect them either visually or with sonar, and that's what we did. And so we were going to do it initially visually with a camera. So our own camera wasn't connected, but we put a GoPro camera on, and this is how we synchronized the time on the frames of the cameras by shooting a clock, so that we can synchronize the camera data with what's going on with the data that we collect, on the AUV. This is me coaching a graduate student through AUV mission planning. This is Nicole, totally bored or seasick, I'm not sure which. This is Nicole, no wait, this is Nicole annoyed with art, who has the camera. These are some of the support guys that were out there helping us from SRI. It's a beautiful day. This is the AUV with the magnetometer on the front. So we have a little clip on the bottom of the AUV that we can put a GoPro camera in. That's what this is taken from. And then in case you're curious what it looks like from an AUV's perspective to get deployed. Don't worry, Art, I got the heavy end. And a 1, and a 2, and a... Woo! So I don't know if you can hear that. This is kind of fun. That's the inertial navigation system making all that racket. Ooh. listened to that long enough, we'd hear the acoustic modem and the screw spin up. And then once we got down to the bottom, of course, we couldn't see very much of anything. Like it was just too turbid. Unless you got really close. Yikes! There it goes by one of our targets. So that was maybe a little closer than we should have been. One of our other missions, our other goals was to have, of course, really close data density. We wanted line spacings that were just a meter apart, so that we had a chance of detecting those smaller targets. And it wasn't until the drive down in the car, I'm playing around looking at missions and thinking about how we're going to do it, that I looked at a mission planning file for the AUV. And it turns out it doesn't have enough significant digits to even plan a mission such that the spacing's 1 meter apart. So we were sort of shot right from the get-go. And then another issue is that the AUV runs missions waypoint to waypoint, and it doesn't consider like the cross-track distance off of a line that maybe you set out. So, and the way it knows it got to a waypoint is it's within some sort of distance of the waypoint, and I think it's actually set to 10 meters. And you can make this smaller, but there's a danger in doing that because the AUV will just go round and round and round trying to get to a waypoint. And the problem with this is that if the AUV comes in from a funny angle, it doesn't actually pass through the waypoint and then heads off towards the next one, and there's a long track offset from where you want to be. So you've got to plan your missions in a way that the waypoints are sort of way outside where you want to go. Of course, as you get closer to the waypoint in the end, that offset closes, but it's just another factor. When things fall off as the cube of the distance you are away, you got to kind of think about those things. So our ability to assess the navigation, our effort to assess the navigation was done with the side scan. This is 900 kilohertz marine sonic side scan, and you can ignore this plot. Right there you see the return from one of the floats, and this dot, these dimensions are meaningless in this picture, but this dot is the location in the side scan, assuming a flat bottom, where we know the actual thing to be. So that's where it should have showed up. And of course this wasn't straightforward because there's not enough significant digits in Marine Sonic's own navigation file to discern, well, to make a smooth path. That's the blue, and the green is the INS. So we had to completely re-navigate all of the Marine Sonic's data to get a smooth path. And then you can see one of the returns in the water column from one of the floats. And here you can see there's a float and then the target down beneath it. And I went through and picked out each of these and all of the side scan data, and the sort of cloud of points there are where my picks have been in the past on previous runs, because of course we're going around and round in circles, passing over the same place with the side scan a lot, because we're only moving over 2 meters each go. So we get lots of passes over all of that. And if I plot all of the errors between each of those passes and the known positions, this is the error in easting and northing, and this is -1 and +1 there, and -0.5 and +2.5 there, if you can't see. But the interesting thing about this plot is, although there's a lot of noise in this plot, and that's probably due to my own poor picks, there's not really any net drift to this. And it turned out that although our whole survey might be off by as much as several meters, it was completely self-consistent, and you could take the survey and just shift it and it would match up exactly with where we knew all the known targets were. So based on that, we said we met our positioning requirements because sort of absolute positioning requirements, because we felt that operationally you could put seed targets out, you could survey them in, and you could use this technique to kind of shift things. And as long as you keep the survey area small enough, like in this case 100 meters by 100 meters, it would be a worthwhile, it would work. This is what some of the data looks like if you grid it up. I don't think this is diagonally corrected. That's what the sort of long-term trend you see kind of across there. But this was a survey at 2 meters off the bottom, and this was a survey at just 1.5 meters off the bottom. And it's the same location, exact same survey run. And you can see little blips and the data and some more defined blips here. And those are some of the seed targets. The folks from geometrics can take that 1.5 meter data and then predict what you should see at 2 meters and predict what you should see at 3 meters, so we can get an idea of what size targets we ought to be able to see if we have to run further off the bottom. It was like brutally flat here and easy to run pretty close to the bottom, but any place that there's a lot of terrain, you just won't be able to do that. I overlaid on the data here pink dots showing where the true positions are, and this is the same thing on the other side. And we pretty much detected everything in the blind grid that was out there, and there were 3 other big giant anomalies that don't coincide with any of those pink dots. One of them was a target that the SRI guys deployed that they didn't tell us about, so it was like a double blind. The other 2 were anomalies that were just there on the seafloor that we just happened to detect. So in the process of doing this, I was like not annoyed, but you know, that this data wasn't diagonally corrected, and I realized that I could remove a bunch of that by just taking the first derivative of all of this. So I made a plot of the first derivative, sort of the long track derivative of the magnetic sensor recordings, and that's what you get there. And I actually think that, I mean, part of the challenge of picking out targets in this is just the color scale, but I actually think that this is actually easier to pick them out of. The folks that do this for a living have their own commercial software. I mean, they didn't write it, but they buy commercial software for processing it. This is the kind of data product that they produce. And every place you see a circle on here is where a target is supposed to be, and every place that you see a plus is something that was detected. Of course, there's a bunch of targets here that were detected that weren't things that were deployed. There's like a 155 millimeter guy that's supposed to be right there that we didn't detect anything from. And I actually think that is the one that this one here got, that was like the double blind guy. It was not in the right place. So in the calibration grid, this was at 2 meter altitude. We had this table, and I just stuck it in here because we didn't actually detect a lot of the 60 millimeter, the smaller shells. But so getting close to the bottom is an important thing. And part of that was because we actually couldn't run 1 meter line spacings. There wasn't enough resolution. All right, so that's pretty much all I have. In summary, we had a great time, and we were able to put this contraption all together and go out and collect some data and have a bunch of operational modes for both operating the AUV when you do these surveys, but also new methods of doing compensation for magnetometer data that include the current terms and allow you to handle issues over the discharge of a battery. And yeah, it's been a really good project. So I'm happy to take any questions.
What is your assessment of the probability that this will eventually work? I assume you're partway through the project.
Yeah, we're far enough along that Geometrics is advertising them, and we've got an RFP from the Portuguese Navy, I think, to buy one. I mean, it doesn't come to us, but they asked us for training on it, and so we'll probably provide them training if they actually purchase one. There's a lot of people actually that have inquired with Teledyne about these. A lot of interest. I think there's a lot of work to be done for unexploded ordnance kinds of stuff in lakes and offshore. But yeah.
Why don't you tow the Maggie after the AUV to eliminate all the noise that it creates?
It's an interesting idea. I think it's logistically hard to do. Like, how do you keep the tow line out of the screw and
It's your problem.
Yeah, fair enough.
Well, but think about how airplanes do it with a Stinger. I mean, you have a plastic rigid. That's just the way it's done on a P3 or something like that.
Yeah, I mean, effectively, that's what we're trying to do with the flooded section up front, is to have something that sticks out front. We just don't have it as far away. We have to consider a little bit of the dynamics of the vehicle and how it flies. Once you get a really long vehicle, once you get into a current, it tends to porpoise a little bit. But it's something that we've thought about. In fact, what the guys are really more interested in is how to put a gradiometer on. But to do that, you can't have it like, you can't have, it's like two magnetometers for which you calculate the difference between the two measurements. But you can't have it inline, you gotta have it across track. So, and nominally they say, because what you measure inline, you could fabricate from your own single sensor as you go along. So you gotta have it across track for it to be of any use. And sort of the rule of thumb that I've been given is like a meter is probably a minimum distance between the two for it to be useful.
Catamaran. A two AUV catamaran.
Yeah.
With all your sensors in
Yeah,
between.
that'd be fun. Yeah, I was thinking like a hammerhead shark kind of.
But you said that if they're inline, say that again, that because you're just measuring it at a delta T for the first measurement and the second?
Yeah.
But all marine radiometers that are towed are inline. We towed one around for years.
Ideally, you want them perpendicular to the magnetic field, the local magnetic
You
field.
might want to, but we did it and got much better magnetic measurements.
I plead ignorance. I don't know.
I'll be darned, that's really interesting.
I mean, just sort of. I mean, you can imagine if you have a high enough sample rate, you're going this direction, then just delaying the sample and taking the difference between the two will give you the same thing as having two sensors that you're actually moving like that. So, it wasn't.
I thought some gradiometers actually use three, and one had to be orthogonal.
Well, the one that geometrics sell, the marine radiometer, is a cross track. Yeah, but usually, I mean, the point of it is to get it perpendicular to the local magnetic field so that you can remove that component. so.
We just towed them.
Maybe somebody
Two.
wanted to sell you
Yeah,
two
three.
magnetometers.
Yeah.
Must have made up a lot of data.
So, talk about the advantage of this over sort of the more classical approach to towing a magnetometer on a raft or something like that in these counties, the gradiometer types, I guess they're
Yeah,
typical.
I think the big issue is how close you can get to the bottom without and at what speed you can do that. It's not something that I do for a living, obviously, so I'm not sure that I understand all of the arguments, but I think there are places where and maybe the other issues. I mean, I don't know how explosive this stuff is, and if you bonk it with the magnetometer or the AUV, how likely stuff is to detonate. But you could imagine places where you'd rather send the AUV in than a boat with tow gear.
Well, the boat could be autonomous also.
That's true. That's true. The other issue, I suppose, is positioning, and you could argue, I would argue maybe, that we can position with the kind of stuff that we did. Maybe that's not feasible everywhere, but we can position stuff pretty well. In 100 meters by 100 meters, I mean, we can get to less than a meter in positioning. And you can run it out there and you don't have to be, like, when people, I guess that's the other issue, like, let me back up. When people, like, these are 2 meter lines between these, and we're running a racetrack around, and this is like 30 meters across or something like that, from one goes to the next, and nobody in the right mind is going to do that for an hour and a half or 2 hours in a boat with a tow body that they can't position to this well on the bottom. And at least with the AUV, we can do a very systematic survey, some flaws in it, but a very systematic survey across the space, and the consistency of the data across here, I think, tells me that within like in a relative sense, our survey over this scale is actually quite good. So that's an advantage, I think, as well.
I'm sorry if I missed it. Were any of the targets buried?
No, none of them were buried.
Because one would think that, there's where the advantage comes.
Yeah, if you're getting close to the bottom, again, the closer you get to the target, if it's buried, then you gotta get down there. Yeah. Other questions? Anybody else?
Do you think you can always do your positioning that well, or you just happen to in this particular case?
On 3 or 4 surveys of this scope, all of them were self-consistent. We had to move them in different amounts. One we only had to move about a meter, but another one we had to move 6 or 7 meters. And that's kind of in the range of what you'd expect from a WASP GPS that may or may not be getting the WASP corrections So there's like two components to AUV positioning. There's the fix that it uses right before it submerges, basically, and the uncertainty involved in that, and then how that grows as it goes underwater. And so in this case, we're seeing the error in that fix getting propagated all the way to the end with some growth while you're underwater. But that 1% of distance traveled, so actually I'm kind of embarrassed about this. I learned this in AUV boot camp because I totally misunderstood that spec. But many INS manufacturers quote the ability of their navigation systems as a percentage of distance traveled. And I always thought that was linear distance that the AUV had gone, but it's actually not. It's radial distance from the point that it's submerged, because a lot of the errors that you accrue going one direction, you remove coming back the other way. So you don't remove all of them, but so 0.1% of distance traveled over 100 meter by 100 meters isn't going to give you more than a meter's worth of error from the INS alone. So that's totally in spec, and for those reasons, I think over small survey areas, that kind of navigation performance should be repeatable.
And this kind of survey just lends itself ideally to a kind of a SLAM type approach.
Yeah, it does. I mean, like everything that I do these days is trying to figure out and understand the proper math for doing that kind of stuff and how it might work. And but yeah, I completely agree. I mean, what I did was, I could have corrected based on the data that I had. I think there's a lot of noise in the data that I had.
The problem when you're looking for unexploded ordnance or something that you don't know is that you're making an assumption about consistency that may undermine your basic purpose.
That's absolutely.
But if you have any sort of natural targets within there, with that kind of survey,
And we also did go out and collect bathymetry data with the geoswaths, and our intent was to use that as well. But I don't think you would want to, put the geoswath on here with the magnetometer, because I think every time that thing pings, you'd see it in the magnetometer data. It'd be nice to have a bathymetry data set that you could use for SLAM. Yeah.
Do you have any plans to repeat any of these experiments once ARTS Gavia gets back?
Yeah, I mean, all of this stuff was with ARTS, like all the stuff in March was with ARTS Gavia. So yeah, it was only at the Naval Academy that we used their Gavia. So yeah, we've done it all with ARTS Gavia since, and there is follow-on work planned. There's a bunch of stuff that the geometrics guys would like to twiddle with about different ways of doing compensations and whether or not. So remember I told you there was that electronics problem and we thought it was the INS, so we moved the INS back and moved the battery forward. So the battery was right next to the magnetometer module this whole time, and now that we know that that's not the problem, we'd like to move the battery back and the INS back forward, knowing that the battery's got all the current coming out of it, and that should help with things a bit. So yeah, so there's other efforts to do that kind of stuff, and some mechanisms within the funding stream for follow-on work that should allow it. Yeah. Unless anyone has any more questions.
Thanks again.
Yeah, thank you.